So today we're going to talk about side channel attacks. It's presented by Dan Banzer. So the agenda for today, what is a side channel attack? How does a side channel attack work? The side channel attack methods, like what types of attacks are there out there? And then some countermeasures, how to prevent these side channel attacks from occurring. And then we're going to have a little short demonstration of some of the components used in side channel attacks, some physical components. So what is a side channel attack? So a side channel attack is a security exploit that attempts to extract secrets or data from a chip or a system. This is achieved by measuring or analyzing various physical parameters of the chips or systems. Examples include such things as electromagnetic emission, what chips can give off or computer screen gives off, supply currents, or execution time of code. Side channel attacks pose a serious threat to modules that integrate cryptographic systems. That's a main exploit that they go after. So how does a side channel attack work? So a side channel attack does not target a program or its code directly. It's not going after the software side. Instead, it attempts to gather the information or influence the program execution of a system by measuring or exploiting indirect effects of the system or its hardware. Simply, a side channel attack breaks cryptography by exploiting information inadvertently leaked by a system. So it can be stuff like that EM radiation that comes off of things, or acoustic noise that comes off of different components. So this graphic is just showing plain text going in, and then security key used to encrypt, and then the output, you got your encrypted text. Well, the side channel attack targets the chips, could target capacitors, and it measures power consumption, timing information of programs running, and then it's able to analyze that data, and they can get stuff like the security key out and then unencrypt the data. So power analysis is one type of side channel attack. We're going to go over a few different types here. This picture right here is showing a setup that actually is measuring the radiation that's coming off of the chip when it's in use. And then they're able to go over that information and pull data from it. So a differential power analysis. This is a statistical method for analyzing power consumption to identify data-dependent correlations. This approach takes multiple traces of two sets of data, then computes the average of these traces. If the sets are correlated, then the difference will be a non-zero number. Given enough traces, even tiny correlations can be seen, regardless of how much noise the system is producing, besides the traces that they're looking at, since the noise will effectively be canceled out during the averaging. Analysis methods such as this can be used to extract bits of data from the stream that they're looking at. So another one of the attacks for side channeling is called a Van Eck phreaking, which is a really interesting name. I like the name. And this picture is just kind of showing a graphic of what it is about. So Van Eck phreaking, also known as Van Eck radiation, is a form of eavesdropping in which special equipment is used to pick up sideband electromagnetic or EM emissions from electronic devices that correlate to hidden signals or data, and then used to recreate these signals. Sideband EM radiation emissions are present in tons of stuff, basically anything electronic, like keyboards, computer displays, printers, pretty much anything that has an electrical signal, that electronic device. In 1985, Van Eck published the first unclassified technical analysis of the security risk of emanations from computer monitors. The paper caused some consternation in the security community, which had previously believed that such monitoring was a highly sophisticated attack only available to governments. But Van Eck successfully eavesdropped on a real system at a range of hundreds of meters using just $15 worth of equipment plus a television set. Then in 2004, academic research revealed that flat panel screens and laptop displays were also vulnerable to this type of attack. And in January 2015, the AirHopper project from Georgia Institute of Technology demonstrated the use of Van Eck phreaking to enable a keylogger to communicate through video signal manipulation, keys pressed on the keyboard of a standard PC to a program running on an Android cell phone with an earbud radio antenna. Another type of attack that we're going to go over here is acoustic cryptanalysis. So this type of attack, a side channel attack, exploits sounds emitted from computers or other devices. So most modern acoustic cryptanalysis focuses on sounds produced by computer keyboards and internal computer components. But historically, before the modern types of attacks, they were applied to like impact printers, stuff that made mechanical noise, or electromechanical deciphering machines was another one. So in 2004, researchers at IBM Almaden Research Center announced that computer keyboards and keypads used by telephones and ATMs are vulnerable to attacks based on the sounds produced by the different keys. Their attack employed a neural network to recognize the key pressed. And by analyzing the recorded sounds, they were able to recover the text of the data being entered, such as when people were typing in their PINs or passcodes, passphrases, passwords, all that type of stuff. So also in 2004, Ada Shamir and Aran Tromer demonstrated that it may be possible to conduct timing attacks against a CPU performing cryptographic operations by analyzing variations in the acoustic emissions. The emissions were ultrasonic noise emanating from the little capacitors and inductors on the computer motherboard. And then in 2013, along with another researcher named Daniel Gengen, they published their actual successful attack on a laptop running a version of GNU-PG, which is an RSA encryption implementation. And they used both a mobile phone that was right by the keyboards or a lab-grade microphone located up to 4 meters away they were able to capture. So acoustic emissions occur in coils and capacitors because small movements when a current surge passes through them, so they actually expand a little bit and they give off acoustic noise when current goes through. Another attack in March 2015, it was made public that some inkjet printers using ultrasonic heads can be read using high-frequency microphones to record the unique acoustic signals from each nozzle and using timing reconstruction with the known printed data. So this hack actually happened in the real world where hackers implanted a microphone, chip storage IC, and a burst transmitter with a long life battery into doctored cartridges for the inkjet and substituted them for genuine ones, and sent these by post to whatever targets, and most of them were banks. Then when they were used up, they retrieved the cartridges from the garbage because they had RFID chips in them to be able to track them down. All right, so let's go over a few countermeasures and there's a whole bunch more, but I narrowed it down to 5 to put in here. So jamming the emitted channel with noise. So that's basically just saying whatever avenue that the noise is coming out of, add additional noise to that to make it more difficult. Random delays are introduced to deter the timing attacks, so they can't base keystrokes, or when something's being encrypted, they can't pull data out from that. So this arbitrary or the artificial noise forces attackers to collect much more data, and it just wastes their time, makes it a harder target. Keep a consistent memory access pattern regardless of input. So constant execution flow is strictly required, meaning when you have a program running, make sure that the program is smooth throughout and doesn't have peaks and valleys for what type of data it's using at a time. So analyze and evaluate. So all electronic systems should be carefully evaluated with test vector leakage assessment to identify sensitive side channel leakage. So Rambus is a company that does this, and they're able to test all the systems to see what is being leaked out of them through the physical components. Eliminate the relationship between the leaked information and the secret data. So apply binding technique. So this technique alters algorithms input into an unpredictable state to prevent leakage. And electromagnetic emissions can be blocked using signal attenuating materials such as copper, aluminum, or steel. It's basically building mini Verde cages over components to shield the EM fields that they give off. Power line conditioning and filtering are often used in conjunction with this technique. So we're going to go over a little demo, and before this starts playing, this distance is actually up to the 4 meters that was needed to be able to capture the key logging accurately. So I started 4 meters away, and then as I walk up, I just have a cell phone next to the keyboard, and they use the microphone on the cell phone also to capture key logs accurately and be able to recreate what was being entered. So then I'm going to open up this computer, and it is an older computer, but you can see the capacitors I'm going to show here, and like the capacitors right here by the memory. This is ones that could be measured to be able to see what memory is being worked on. Same with the CPUs, and capacitors on this side can be used to be able to see what is being used in the CPU. So there's a lot of good data out there, and a lot of good resources. So I put a few in here in the references, but I would encourage everybody to go out and look into this, because there's a couple of these references are actual white papers that go into a huge amount of detail on how these attacks work, and it's a little more complicated than I could explain here because I'm not a matter expert on this. So I'd advise going out and reading these articles because they're very interesting, and it gives you a different perspective on cybersecurity, and not just protecting the software, but the interesting attacks that can occur based on physical components and just what they do naturally in the world. All right, thank you.